So we saw in the last module that a mutation can change the genetics in a population, and they might continue to be present, or it's possible this organism doesn't reproduce, not because it's worse, not because it's less fit, just sometimes organisms don't reproduce. And it could disappear, and again, that could also be evolution by mutations. Okay, so the mutations can come and eventually they can go. That's evolution by mutations. Is it predictable? Well, let's go back. If we started in this scenario back here, could we predict what organism is going to have a mutation? No, not really. Can we predict what gene is going to have a mutation? Nope, can't predict it. Can we predict which nucleotide in that gene is going to have a mutation? Nope. Can we predict what nucleotide it's going to mutate to? Can't predict it. So evolution by mutations, 100% unpredictable. This is random evolution, just random changes in DNA. Now, here's the fun, is that it turns out that although I said mutations are rare, meaning they happen every 1 in a million to 1 in a billion nucleotides that get copied, turns out they're incredibly common, inevitable, guaranteed to happen. And here's why. Is that for a population, a species, and again, by now you know when I say population, we mean species. For a species to evolve by this mechanism at some point in their history, well, let's look at them. Your typical organism has a lot of DNA. They have a big genome. There's a lot of genes. Any nucleotide in those genes is an opportunity for a mutation. So even within an organism, there's a lot of possibilities for a mutation. Populations aren't just one organism. There are thousands or millions of organisms. And for the species to evolve this way, it only takes one organism out of the many to have a mutation for the whole species to evolve this way. And we're talking about evolution, so really we're talking about reproduction. And so the mutation could happen for this baby, or maybe another baby, or maybe a later baby. Since lots of organisms reproduce throughout their lifetime, it doesn't have to be one baby, it could be any baby among any of the organisms. And populations don't exist today. They're still around a year from now, in a decade, in a century, in many cases, hundreds of thousands of years. And for that species to evolve by mutation, you just need one mutation at one time in one baby that was born once. And because these are big numbers, rare things turn out to be inevitable. It's sometimes called the law of large numbers. I'll put it this way. Have you ever won $1 million in the lottery? I haven't either. I guarantee you haven't. Well, okay, I can't guarantee it. I'm 99.999999999% likely that you've never won $1 million or more, and probably don't know anyone who has. Okay, but has somebody won? Yeah, because there's a lot of people playing lottery. Could it be somebody in Illinois this week? Guaranteed somebody won $1 million in the past week. Don't believe me? Go to the Illinois lottery, check out the history. They tell you that. Okay, for big wins. Um, that's simply because there's a lot of people playing, often many times, and it's a big state with a lot of people. The chance that it's you is basically zero. The chance that it's somebody, well, there you got the law of large numbers. It's guaranteed. And here's my favorite example. I invented this, but this is like, gives me such a thrill. Let's see if you are that lottery player. And we're not going to talk about numbers here. We're talking about like real stuff, evolution. So each of us is a human, and humans have about 3.2 billion base pairs, nucleotides, 3.2 billion from mom, 3.2 billion from dad. They basically come together in their chromosomes. This is the genome, and any one of these is an opportunity for a mutation. Now, we're only going to look at mutations that can result in evolution. Okay, so we're going to get rid of all the skin mutations, all the other mutations that can happen, especially from the sun, from the ultraviolet radiation, lots of other things. We're going to focus on the ones that potentially involve evolution. So we're only going to look at mutations in babies. And on Earth today, in our single species, there's something like 250,000 or 1/5 of a million babies born every day. Another 200,000 tomorrow, 200,000 after that. These numbers are a bit dated now, but the numbers are basically the same. Okay, we have to multiply each opportunity for a mutation by the number of DNA in each of those successfully born babies every day. We do the math, and don't forget, mutation could have come from mom, Could have come from dad. So we have to multiply this because the mutation in the babies is doubled because there's a DNA from mom and a DNA from dad. We do that. This is how many new copies of DNA are born today that did not exist on Earth yesterday. And if you do the math, millions, billions, trillions, 1 1/3 quadrillion nucleotides now are born, have a birthday today that did not exist yesterday. And another 1 1/3 trillion tomorrow, and the day after that, and the day after that, and the day after that, for hundreds of thousands of years if our species is lucky. Now, how rare are mutations? Well, here's a rule of thumb. And I've learned that as we're learning DNA, this is probably not accurate, but it's a good enough rule of thumb. So a good rule of thumb is that if you have a nucleus, the way DNA gets copied in a nucleus has some additional kind of mechanisms to make sure the two strands are aligned. There's some extra enzymes involved. Um, and so the rate of mutations, if you have a nucleus, on average, we think is a little bit rare. So let's say 1 in a billion. Okay, because also the nucleus kind of helps protect the DNA from ultraviolet radiation, thing that can cause mutations. So for both of those reasons, if you have a nucleus, mutations are really rare, 1 in a billion. If you don't have a nucleus, the cell's going to be smaller, the DNA is more exposed to things that could cause a mutation, and the way the DNA gets copied is a little bit simpler, and so it's possible that it can have more mutations. Okay, so let's say if you have a nucleus, it's 1 in a billion, very rare. If you don't have a nucleus, like your bacteria, it's much less rare, 1 in a million. Well, humans, we have a nucleus, so let's use about 1 in a billion. That seems to be pretty close to what humans' mutations are. So we have to do the math here, divide it. You don't have to do this math on your own, just kind of follow along. And when we do the math, this is how many new mutations had a birthday in the babies that were born today. 1 1/3 or so million mutations exist in our species that did not exist yesterday, and another million tomorrow, and a million the day after that. And these babies were perfectly healthy by and large when they were born, which means these are perfectly good mutations. They're not causing the baby to be diseased or to not be born in the first place because the development's working perfectly fine for the baby to be born. What that means here is that there's a lot of evolution by mutations in our species. Now, are you a mutant? Well, let me ask you a question. Are you a human? Yes. Were you a baby once? Did you have a birthday? Yes. Do you have DNA? Yes. Do you have two biological parents? Yes. Okay. Do you have a nucleus? Yes. Well, let's see. Every day there's about 200,000 babies born, and there's about, let's round it, 1.4 mutations, 1.4 million mutations. What that means is, on average, each of these happy babies that their parents love every day has about 7 mutations. Let me put that another way. On average, every baby is a mutant. You're a mutant, I'm a mutant, my brother's a mutant, trust me. All of my relatives are mutants. And not only are we all mutants, but we inherit the mutations of our parents. Our parents are mutants. So we're not only the mutant from our parents, but we inherited our parents' mutations, and they inherited their parents' mutations, which means a lot of your DNA is mutations, some that were unique to you, some that are unique to your immediate family, some that are unique to your less immediate family. And the basis of these mutations that everybody has on average, some have more, some have less, but on average a lot, is the basics of forensics and paternity tests and all of the DNA technology that helps us identify humans based on their DNA. It's these mutations. The bigger story is not that mutations are common, even if the chance that each individual DNA is going to have a mutation is low, but that every species, every time a baby's born, has evolved by mutations. This idea of evolution by mutations basically guarantees that every time babies are born, tons of mutations, which means that this is happening all the time. Now, if you think about this and this idea that you and me are mutants is uncomfortable to you, you're not comfortable being a mutant. Occasionally in class, there's like that student who you like, they're like, I knew since I was born I was a mutant. Well, it's like we all are, not so special anymore. Um, but if you feel uncomfortable knowing that you're a mutant, that's probably because you were told that mutations are errors, they're mistakes, they're problems in DNA. What this suggests is quite the opposite. Mutations have no effect at all. If you don't sequence your DNA, you don't know you have them. They're what we call neutral. They have no effect at all on your health, on your ability to survive, on your ability to get mates, on your ability to reproduce, and your offspring have a good chance of inheriting them as well, and they will not harm them. They will not hurt them. They will not make them able to fly or be superheroes. They're just going to be there. And you've got a lot of these. This idea of neutral or harmless mutations, the theory is sometimes called the theory of neutral mutations, that populations are filled with enormous amounts of variability that doesn't do anything at all. It doesn't make the genes work worse or less or better. It just keeps on chugging along. The key here is if the environment changes, what was once a neutral mutation could turn out to be beneficial or harmful in a new environment. I've got weird ears, so do you. What's the value in an adaptive sense of having big or fleshy or loby ears? As far as we can tell, there's no adaptive value, but it's genetic. It's probably mutations that because they don't affect you, they just show up, they get passed on. And if the environment changes where suddenly having big lobes turns out to be the key to survival, then those neutral mutations could turn out to be beneficial. As long as they stay hidden, there but having no effect, evolution by natural selection can't get rid of them. Now, occasionally they will have an effect. Maybe a mutation happens that doesn't cause the baby to develop properly, in which case it doesn't get born in the first place. Or maybe it causes a disease, what we call a disease, but it's a genetic change. Or maybe down the road when the organism is much older, it has an effect. We call those mutations deleterious. And if it does have an effect, and in evolution, what we mean by having an effect is that if you have that mutation, you're less likely to survive as long as everyone else. You're less likely to have as many babies as everyone else. That mutation will now be visible to natural selection, and that DNA will disappear over time. It will be selected against. And once it's deleterious, we're not talking about random evolution. Now we're talking about selection. And here we can predict if it is deleterious, it will become rarer. Inevitably, there will be some mutations that are beneficial, meaning that if they have an effect, it could increase the number of offspring and survivorship, which means that those DNA will now also be seen by natural selection or sexual selection or human selection, and they will become more common over time. These last two processes, once the mutation has an effect, it started out by neutral evolution, but once it has an effect, we're now talking natural selection. So this mechanism of evolution by mutations is only talking about mutations that don't have an impact. They are neutral. They have no impact. And just to end this story here, just to show you how rampant genetic variability is. And if you wanted to know where your mutations are, you'd have to spend about $10,000. I bet within a decade it'll be 1,000. You could get all of your DNA sequenced, your brothers and sisters for another 10,000 per person, your parents' DNA, and you could find out exactly where those mutations are. We're getting to that point. That's part of evolutionary medicine or personalized medicine. Personalized medicine is really genetics. To give you a famous example of how much amazing variability is in a population and it's neutral. This is a population of weedy plants that live in the Mediterranean, and it's the ancestral species that all of these other varieties, all of these are technically the same species, that once humans saw the natural variation that was present, they'd say, well, let's focus on the leaves and select for leaves. Well, okay, collards and kohlrabi, or Brussels sprouts, or florets. We're going to get cauliflower or Brussels sprouts and cabbage, or kale, different color variations. Or let's focus more on tight flowers, and we're going to focus on broccoli and cauliflower. These are all the same species, but geneticists, through human selection, have taken whatever rampant natural variation there was and selected out different genetic populations as we want them. This is the power of variation combined with natural selection.